So we'll continue on here. This is our good friend Pierre Sadi Carnot, considered one of the fathers of thermodynamics. In his work, as I understand, I'm not a huge history person. I know just a little bit here and there about where some of these individuals came into play and play into history. Um, Carnot was what he proposed was pretty revolutionary. If I'm not mistaken, he was a French military engineer. I think this was in the time frame somewhere around the Napoleonic Wars. But basically, the idea was if they could come up with the most efficient engine, they could probably rule the world. But definitely that was the goal of most people in this time frame was add these steam engines. It's really kicked off the Industrial Revolution. We want to make the best steam engine we can. How can we get more and more efficiency out of these things? Carnot in 1824 proposed at the time what became essentially the theoretically most efficient cycle that could be proposed. And I always like to show pictures of some of these individuals. Thanks, Wikipedia. This is just a Wikipedia image. And the terrible head joke I always tell in class is I like to show these individuals. So when you're really cranking away at your homework and you're spending hours, I mean, if you're doing this right, you're not just letting AI or some service do your homework for you. If you're really wrestling with these problems at some point you should be frustrated. It's like, so tired of this. Why did I choose to be an engineer, right? It's just don't hate me. I didn't do it. And it's this guy, that guy right there. It's his fault. His fault, right? So when he is the source of your ire, not me. Okay. I'm just the messenger. That's the guy. That's the guy. If I can get this mirror straight on the camera. No, I'll show you some of our good forefathers of thermodynamics. This is one of them. This is Pierre Sadi Carnot. Let's talk about what he did. I mean, why do we not like this guy? Well, what am I going to do here? So I'm going to talk about I'm going to show these processes graphically on a PV diagram here in just a second. I guess I could draw it here. I'm going to just draw this on paper. Okay. So I'm going to stop share here and I'm going to change video. Okay. And so remember, or I guess I should say, um, before I stopped sharing screen, I said, well, there's these four processes. I showed you the four processes for the Carnot cycle. Carnot proposed this process. And if we plot these on a PV diagram, pressure versus volume diagram, he starts out with an isothermal expansion. So we're going to go from a small volume at state one to a larger volume at state two. Now, in class, I would stop and I would ask, hey, what does this area under here represent? Who can tell me what does this area under a PV curve represent? And people would say, well, that's potential work. That's potential work that we could get out of the system, right? Yes, that is potentially the work that we could get out of this cycle. Now, this is occurring, this process is isothermal expansion. Isothermal meaning constant temperature. That's occurring at a high temperature. Okay, so a line of constant high temperature going across. Okay, and then after isothermal expansion, we would go through another expansion. This would be adiabatic expansion. So if I basically supply enough heat to keep the temperature constant, but then I stop supplying heat to get down here to state 3, what's going to happen is this process is going to end up going along a line or down to a line of lower temperature, right? And now, if I were in class, and I guess I could do it here, I would do this on the board where I could erase these things. I'm going to do these in green. These lines are going to be all in green. This whole area underneath there, that represents potential work that we could remove from the system. Now, those are the expansion processes. So isothermal expansion, adiabatic expansion. So I from 2 to 3, I'm expanding, but I'm not allowing it to lose or gain heat. By doing that, I end up dropping the pressure and dropping the temperature to get the expansion to occur. Now I go back, though, along the line of constant temperature from 3 to 4. I do an isothermal expansion, I'm sorry, isothermal compression. So this down here, that's compression. Notice these areas up here, these are green. These are expansion, that's work out. This area here, that's work in, that has a negative sign. So it's going to get, this area under this curve gets subtracted. And then to complete the cycle, I do an adiabatic compression. So I compress the system, but I don't allow it to gain or lose any heat. And by doing so, if I compress it adiabatically, it's going to end up increasing pressure and increasing temperature up there to the higher temperature. So all of this area down here gets removed. What you have is this area bound by these curves. I'm going to color that all in green, if you can see colors. And the area bound by those curves then represent the potential work that can be extracted from this process. Right? So again, expand isothermally, expand adiabatically, compress isothermally, compress adiabatically. And I've got this in kind of a graphic format, right? Expand isothermally from 1 to 2. I've drawn that up here, right? This is I stay down here. This is where most of the work in the engine can come from. Expand it adiabatically from 2 to 3. Right? That's this guy. That's where the temperature drops to the lower temperature. We're going to compress it isothermally. Again, isothermal meaning constant temperature. So we're going to go to a smaller volume along this line of low temperature. This area under this curve is now negative. So I've got positive minus the negative. So that difference goes away. And then finally, to complete the cycle, adiabatic compression, get back up to the initial state. So why do I draw this and do all the coloring? Because notice the process here. So the net work, and this is what we call, I call this a cyclic integral. I know sometimes we call this a line integral, but what this means is this is an integral that is along a curve. And in this case, that curve has limits, the same final and initial limit on this integral. So it's going from an initial state all the way around back to that initial state. So notice the sign on each of these integrals here, right? The expansion from state 1 to 2, that's positive. The expansion from state 2 to 3, that's positive. And the compression from state 3 to 4, that's negative. And from state 4 back to 1, this is compression from 3 to 4, that's negative. From 4 to 1, that's negative. So positive, positive, negative, negative. And so the total when we add up, again, an integral is, for us as engineers, an integral is just the sum of a bunch of little tiny pieces. When we add up all the little tiny pieces that comprise the cycle to get from here all the way back around to there, we end up with the area bound by these curves. So again, negative sign, the compression indicates work done on the system. That's negative work out. And so you see here, heat is being transferred from 1 to 2, and it's adiabatic from 2 to 3, so no heat transfer from 2 to 3. Then it's isothermal, so heat is being lost from 3 to 4 while it's being compressed, and then no heat transfer occurring from 4 back up to 1. The area bound by this curve represents the net work that we can get out of this cycle. This is a terrible scan from our textbook. I need to get a better scan of this. You could probably Google Carnot cycle diagram and get a much better image of this. But we don't really have an engine that operates in anything like a Carnot cycle. The closest we could do is maybe pretend to take an insulated piston cylinder and remove the insulation out here at the end of it, remove this insulation, expose it to a high temperature heat source, allow it to expand at a constant temperature, and then insulate it and allow it to continue to expand, get it down to a lower temperature, and then remove the insulation, expose it to a cooling sink, a low temperature sink, so it can reject the heat that is not extracted through the expansion process. Get it back, get it to go ahead and compress a little bit. As it cools down, it shrinks, and then insulate it and go ahead and continue compressing it, getting it back all the way back up to state 1. Again, we don't really have a device that does this per se, that I can point to and say, oh, this is a real world version of a Carnot cycle. But there are some things that doesn't mean that we don't use it or we didn't use it as a foundation for other very, very important things. Again, Carnot, when he proposed this, he said, hey, what if we did all these cycles in a reversible fashion? Well, for one, if they're all reversible, that means we could run this thing back in reverse. And if I run it in reverse, now I'm moving heat from a low temperature body, putting some work in, and pushing heat to a high temperature body. If I run an engine in reverse, that's essentially a refrigerator, right? Running an engine in reverse is essentially a refrigerator. And so if the Carnot cycle is reversible, and by definition of Carnot cycle, it is reversible. So if I run that reversible cycle in reverse, now I get a refrigeration cycle, this cycle where I can put work in, the work bound by this curve going in reverse, and now the heat is moving in the opposite direction. Now I'm removing heat at the low temperature, and I'm pushing heat out at the higher temperature. So all that to say, the Carnot cycle can be applied to a heat engine, it can be applied to a refrigerator, it can be applied to a heat pump, because a heat pump is basically a specifically applied version of a refrigerator. So that's one principle that comes out of this. The fact that it's reversible, I can reverse it, and that essentially behaves like a refrigeration cycle. Two other really, really important principles comes out of this, and that this then is used by others after Carnot to really form and flesh out what becomes the second law of thermodynamics, Clausius being one of the main ones here. The two principles that really go on to influence later work is, one, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one if it's operating between the same two reservoirs. So what we find through Carnot's work is really the thing that drives this is the temperature of the high temperature sink pushing QH into the system, and the temperature, the temperature of the high sink source and the temperature of the low temperature sink where the heat is getting rejected into it. These are the two factors that determine the efficiency of the Carnot cycle, and or any other reversible cycle. That's number two. The efficiency of any reversible engine operating between the same two reservoirs, one reservoir at TH, the other reservoir at TL, all reversible engines will have the same efficiency, that being the maximum efficiency, which is higher than any real or irreversible heat engine. So this sets a limit. Again, we talked earlier about the reversible process is considered the theoretical limit. We cannot construct a heat engine more efficient than the Carnot heat engine or any other all reversible heat engines operate at the same efficiency, the same maximum efficiency. And that's where we'll pick up the next video. Well, let's see. What do I got? Yes, that's where we'll pick up the next video.